Hello students, next topic is our polar molecules, as we have to see the effect of placing some dielectric material between the two plates of the capacitor. So before studying dielectric, let us study some of the molecules which are polar and non-polar. What are polar molecules? A molecule in which the center of and positive charge and does not coincide with the center of negative charge, that is called polar molecule. Means positive center and negative center, they are not coinciding, they are separated. And we know that when equal and opposite charges are separated by some distance, they create a dipole. And the molecules which are having permanent dipoles, they are called polar molecules. Means their positive and negative charges, they do not coincide. For example, this is an example of water, and you can see here this is oxygen and two hydrogen molecules, and the angle between, so this is positive, this is negative, negative, and you see these positive and negative charges, they are not coinciding. So here dipole moment is existing from negative to positive. So both of the dipole moments are there, and you see the net dipole moment would be in the downward direction. So means this molecule is having some permanent dipole moment. Polar molecules does not have symmetrical shapes. Examples are HCl, H2O, NH3, CO2, alcohol, etc. Effect of electric field on polar molecules. Now, polar molecules, they have permanent dipoles or dipole moments in them. Now, you see when you place them in the absence of the electric field, all the dipoles, they are randomly oriented and net dipole moment would be 0. So in the absence of external electric field, permanent dipoles of the molecules orient in random directions, and hence the net dipole moment is 0. Means there is no net dipole moment of the molecules. Now, if we are going to apply some electric field, you see initially the dipoles, they are randomly oriented, and when we are going to apply the electric field, then they are going to align themselves in this way. You see, because when dipoles are placed in the electric field, then because of the torque acting on the dipoles will align themselves in the direction of the dipoles electric field in this way. So all the positive charges, they want to go away from the positive of the electric field. So all the positive, they will align, they will go towards the right side, as electric field is in this direction. So in this way, the dipoles, they have aligned themselves. So here the net dipole is not equal to 0. Some of the dipole is going to exist. Dipole moment is going to exist in the direction of the field. So when electric field is applied, the dipoles orient themselves in the regular fashion, and hence dipole moment is induced. Complete alignment is not possible due to thermal agitation. We have not shown here the complete alignment. Thermal agitation is always there. So, but we can say that net dipole moment will exist when the polar molecules are placed in uniform electric field. Non-polar molecules, the molecules which do not have the permanent dipoles. A molecule in which the center of the positive charges coincide with the center of the negative charges, they are called non-polar molecules. They are symmetrical in shape. Examples are N2CH4, O2C6H6, etc. Now let us see what is the effect of electric field on the non-polar molecules. You can see here non-polar molecules. Here These are the electrons. Dipole moment is from negative to positive. Here also dipole moment is from negative to positive. Equal and opposite dipoles, if they are existing inside the molecules, they are going to get cancelled each other. So initially, even in the absence of the electric field, there is no dipole moment existing. So in the absence of the external electric field, the effective positive and negative centers coincide, and hence dipole is not formed. You see here, this is the molecule, non-polar molecule in the absence of the electric field. Now let us see, we have applied the electric field. When we apply electric field, positive charges tend to move in the direction of the electric field. So now you can see here, this dipole is less and this dipole is larger. So even in case of non-polar molecules, when we apply the electric field, some of the dipoles are going to get created. So dipole is going to get created or developed when electric field is applied. When electric field is applied, the positive charges are pushed in the direction of the electric field and the electrons are pulled in the direction opposite to the electric field due to separation of effective centers of positive and negative charges. Dipole is formed. Now let us see what are dielectrics. Basically they are insulators. Generally a non-conducting medium or insulator is called dielectric. Precisely, a non-conducting material in which induced charges are produced on their faces on the application of electric field is called dielectric. So precisely we can say that when dielectrics are placed in the electric field, then charges are induced on the faces of the dielectrics. Examples of dielectrics are air, H2, glass, mica, paraffin wax, transformer oils, etc. So these are examples of dielectrics. Polarization of dielectrics. Now when the dielectrics are placed in the electric field, how they are going to get polarized? Let us see. When a non-polar dielectric slab is subjected to an electric field, dipoles are induced due to separation of effective positive and negative centers. As we have seen in the last slide, that whether they are polar or non-polar, whenever they are placed in the electric field, they will get some dipole moment. So here also, what is polarization? Here, when a non-polar dielectric slab is going to be placed in the electric field, dipoles are induced due to the separation of the effective positive and negative centers. Now, you see, all the non-polar molecules, they are like this. Dipole moment is zero here. Positive, negative charges, they are coinciding. So, there is no charges you can see on the faces of the dipole. But when electric field is applied, positive charges, they will tend to move in the direction of the field, and negative charges, they tend to move in a direction opposite to the field. So you can see here the positive and negative, which are lying very much closer to each other, they are going to cancel each other. So here they will get cancelled. Here positive, negative, they will get cancelled. But you see on the faces of the dielectrics, these negative charges and these positive charges, they are going to get induced in the presence of the electric field. Means inside the dielectric some field will start existing because of these induced charges. Here you can see positive charges, they have appeared, and here negative charges, they are going to get appeared. So some electric field is induced inside the dielectric, and net electric field inside the dielectric will become E0 minus EP. EP is the field which is produced inside the dielectric because of the polarization of the dielectric. E0 is the field which we have applied. The field is reduced when dielectric slab is introduced. So field inside the dielectric will be less as compared to the field outside the dielectric. The dielectric constant is given by, that we have already seen, dielectric constant is field which is in vacuum divided by field inside the material. So here E naught over E naught minus EP. E naught minus EP is the field inside the dielectric. So this is the value of the dielectric constant of this dielectric. Polarization vector. The polarization vector measures the degree of polarization of the dielectric. It is defined as the dipole moment of the unit volume of the polarized dielectric. We know that when dielectric is placed in the electric field, it will get polarized. So how much dipole moment is induced per unit volume is called, this is called polarization vector. If n is the number of the atoms or molecules per unit volume of the dielectric, then polarization vector is n into p, where p is the dipole moment of each molecule. SI unit of polarization vector is dipole moment per unit volume. Dipole moment unit is coulomb meter, per unit volume is coulomb meter cube. So you will get coulomb meter over meter cube, or simply coulomb per meter square. So this is a unit of polarization vector. Now let us see what is the dielectric strength of a dielectric. So dielectric strength is the maximum value of the electric field intensity that can be applied to the dielectric without its electric breakdown. You see, when the dielectrics are placed in the electric field, dipoles are created, dipoles are induced. So the maximum value of the electric field which can be applied to a dielectric without its electric breakdown, that is called dielectric strength. And its value as a unit is same as that of the electric field. So this is the maximum value of the electric field. Otherwise, if the electric field is very much larger beyond its dielectric strength, then positive and negative charges, they will break down, means molecules are going to get breakdown, dipole moments they will be created, but electric breakdown will take place. So this is the maximum value of the electric field which we can apply without breaking down, electric breaking down. So that is the dielectric strength. So SI unit is volt per meter. Its practical unit is kilovolt per millimeter. So these are some of the dielectrics, and the dielectric strengths are given. For vacuum, dielectric strength is infinity. So infinite electric field can be applied to vacuum. Air 0.1 to 1. Porcelain 4 to 8. Pyrex 14. Paper 14 to 16. Rubber 21. Mica 160 to 200. You can see here the dielectric strength is always greater than 1. For vacuum it is infinity, and for air it can be taken as 1. And for any other dielectrics medium, the dielectric strength is greater than 1. So for porcelain, pyrex, paper, rubber, mica, these are the dielectric strengths. So that's all for this dielectrics. Thank you.